Great, thank you very much. Actually, before I start, I would like to thank the organizers of the workshop. So Jennifer, Kenny, and Suelin, thank you for putting on really a delightful workshop. It's, at the very least, for me, it's been a wonderful excuse to come back to Edinburgh after a long time. And I think I've certainly learned a lot, and I hope everybody else has, so thank you. All right, so this is going to be another talk on language, like the majority of the talks on in this workshop. But I think that the lessons, hopefully, that one can draw from this domain are ones that will translate into many other areas as well. I think for me, and I think for many people working on language, one of the attractions of working in this domain is that it's an area in which the symbolic content and activity of us as a species is particularly manifest. And so although there are many things that may be language specific, and figuring out which one's what that is and what that isn't is a major part of the enterprise in our domain. There's also hope that many of the insights that we gain in this area may translate more generally and shed broad light into the nature of the mind. But with that, I would like to talk a little bit, just give you, if you're less familiar with language, give you a bit of specifics in terms of the kinds of linguistic knowledge that has to be accounted for by any model of what kind of knowledge is available and what has to be acquired. So we have, as humans, we have rich knowledge of at multiple levels of linguistic structure, and the knowledge that we have implicates, crucially, it implicates both familiar and novel linguistic content, and I'll explicate this by way of examples. So in the realm of phonology, for example, which is the patterns in how sounds are put together, individual sound categories are put together to form larger units up to the sizes of morphemes and words. There are regularities such as, so for example, this is a word that does not exist in English, dax, and it has you can write it out phonetically as this, dax. And if you pluralize it, if I say, I have one dax here, and if I add a second dax, I will have, everybody knows that the answer is daxes, right? And that has a particular form, a phonetic form that we can write out like that. On the other hand, blick is another word that, it's not a word of English, has a different phonetic form. And if we pluralize that, we get actually a different form. It's predictable. You all know that it's not blickes, it's blicks, right? And so there's some kind of systematicity. This is a highly productive kind of process, and there's systematicity there that we have to be able to account for in terms of our description of the knowledge of the human native speaker of the language. Of course, this is also equally applicable to familiar expressions. So the word trick, this is a word of English. You have experience with it. It has a very similar form to the word blick, which is not a word of English. And if you pluralize trick, you get tricks. Just like if you pluralize blick, you get blicks. Here's another word, goose. The phonetic form looks like this. If you pluralize this, though, you get something different. You don't get gooses like you would get daxes, you get geese. Okay, so although there's systematicity that is applied to both novel forms and to forms that exist in your language, there's also idiosyncrasy, specificity beyond the systematicity. And we have to account for all of these kinds of knowledge that a native speaker has. In the domain of syntax, we know various kinds of things. So for example, there is a systematic relationship between the fact that the string a mouse is part of English and the fact that the mouse is part of English. It's the same systematicity that tells us that a flu is part of English and the flu is a part of English. But you'll notice that these are expressions, they're both familiar nouns, and you'll notice that there's some kind of idiosyncrasy in terms of the relationship between these two, where a flu is somehow sort of maybe more marginal or specialized in the kinds of usage that it would have. And both the systematicity, the relationship between the two, and the specificity of the flu maybe being used in a lot of contexts where A might otherwise be used, are things that the native speaker knows. We can also generalize this kind of knowledge and apply it to novel domains as well. So for example, if I tell you that this is a tufa, then you can now refer to it productively as the tufa. Okay, and so that's syntactic productive knowledge. That's one kind of syntactic productive knowledge. Another one would be that if we have the words missing and marooned, we can combine them to form a coordinate expression. You could coordinate them as missing and marooned, or you could coordinate them as marooned and missing. Both of those are options. Out of curiosity, if you had to choose one, which one would you choose? Who would choose missing and marooned? And who would choose marooned and missing? Very interesting. Okay, I won't comment on that further. All right. So, what are plausible accounts? What are plausible accounts of these various kinds of linguistic knowledge, and how there's some combination of some of it being innately specified and being learned. So, how do we get to the synthesis of innate knowledge and knowledge that is acquired from the environment to the state of an adult native speaker? Well, the framework that I'm going to give you several case studies of today is a framework that you've heard referred to in this workshop several other times. It's the Bayesian learning framework. And the fundamental equation or proportionality relation that Bayesian learning is predicated on is that what a learner does is a learner evaluates various hypotheses, that is, ideas about the structure of the world or the structure of some kind of system, evaluates them and forms preferences over them on the basis of two facts. So in our case, hypotheses are going to be ideas about what the structure of the language that we speak is, the language in our environment. And Bayes' rule says that we form preferences about the hypotheses, the possible sources of the data, the possible underlying structures of the data, based on data in accordance with two rules. So one is the effect of likelihood. So the effect of likelihood says that if a hypothesis does a good job of accounting for the data, that is, it makes the data highly predictable, then I will favor that hypothesis insofar as it makes the data predictable. And the second factor is the prior probability, P of H, which says that I will favor hypotheses that are already preferred for some reason. Already preferred could mean many different things. It could mean that there is an innate bias towards certain hypotheses over others. It could be that experience that I've already predisposes me to certain kinds of beliefs about structure as opposed to others. It's very general. For language-like domains, if once you start looking at really serious chunks of natural language, and I think this is a very important general lesson about the kinds of learning models that we're going to need for all domains of the mind. There are sort of two major features that we need for Bayesian models to really get off the ground and to really be able to learn data in a way that will scale up. One is the notion of hierarchicality. So models have to be hierarchical. And I mean this in multiple senses, and there are two specific senses which are going to be important here. So one is the notion that language has hierarchical structure, and the models actually have to be able to encode hierarchical structure. So syntax involves categories embedded within categories and in rich and complex linearization arrangements and so forth. So that's hierarchical structure there. But there's a second notion of hierarchicality that also turns out to be crucial for learning language and probably for other domains too. And it's the notion of multiple levels of generalization. So what I mean schematically here is that some preference might be influenced by any of a variety of factors that are simultaneously active. Okay, and this in a non-language domain, this might be what people in Edinburgh, the kinds of foods people in Edinburgh do and do not generally like, and this might be, for example, what sort of an average meal of a particular time of the day might be, but there are individual perturbations. So we can represent simultaneously sort of average overall effects of a variety of sort of cross-cutting features, and then idiosyncratic variations at a more specific level of granularity. This turns out to be relevant in language, for example, in terms of how words have grammatical preferences. So some words like certain argument structure frames, some words like certain different argument structure frames. A lot of that is predictable along the lines of many particular features. So for example, semantics is predictive of that, but there seem to be idiosyncrasies that live above and beyond those predictable dimensions. And so that notion of hierarchicality, extraction of generalization while maintaining idiosyncrasy is an essential part of models for this domain. The second notion that we need for language-like domains is the notion of non-parametricity. And what being non-parametric is that the model is not fixed in size. So if you encounter new data in practice, it means that if you encounter new data, then that is not explainable within the rubric of the existing structures that you've got represented, you can posit new structure and assign new structure to that data. Of course, you don't have to, and the general considerations of parsimony and effectiveness of explanation will then guide whether you do so or not. So an example of this, and this is an example from Sharon Goldwater's work here, is this is the notion of what a simple example is a non-parametric lexicon. A non-parametric lexicon is simply one that if you're partway through a series of input, well, you've gotten different numbers of tokens of words in your vocabulary already, what it means for the lexicon to be non-parametric is that if you encounter another word that is not already represented in your hypothesis explicitly, then there is a way of accommodating it as an additional element of structure. What this implicitly means is that actually hypotheses in non-parametric models are hypotheses over infinite sets, the structure that has infinite size, and is it structured within that infinity in some interesting way. So where does this leave us? With respect to nativism and constructivism? Okay, so we have likelihood, we have prior. So it turns out that this is for me why I feel like giving case studies within this rubric is a useful thing to do for this workshop. Is that I think that this approach really it reflects, in order to get these kinds of scaled up models really reflect both nativist and constructivist insights. So there are the nativist insights in Bayesian learning models you could characterize as follows. So first of all, there has to be some notion of what the structure of the hypothesis space is H. What are possible H's? And constraints on what that hypothesis space look like, those are hard limits on the learnable. So if something is not represented in your hypothesis space, then you simply can't learn it. Now, a great deal of work in machine learning in the last decade or so has been on how to cleverly define infinite hypothesis spaces that really could accommodate anything in some meaningful way that you'd want, but do so in a structured and parsimonious way. And what that means is that this is not a strong constraint against learnability of arbitrary structure. This simply says that you may be able to learn arbitrary things, but they have to be represented. The possibilities are still all represented within your hypothesis space. The other part of nativist insight, I think, is that within the hypothesis space, that the prior distribution P of H defines an inductive bias. Okay, so there are many ways of thinking, for example, in language, what grammar is. One way of thinking about it is a set on the actual things that can be represented, and then a set of preferences that you come into the world and into the world of learning language with. That drive you, that incline you toward some interpretations of data and against other interpretations of data. What I like about that is that if you specify it that way, you sort of get you may be able to move universal grammar as a topic from being something that there is controversy over to simply a way of talking about simply a very, very broad class of learning models. On the other hand, there are also constructivist insights in Bayesian learning models. So one is that structure and regularity may emerge as data accumulate. So if you only have a very small number of data points that are not obviously similar to each other, then that may not support the inference that there is a unifying similarity, unifying regularity underlying those data. So if you only have a very small number of regular plural nouns, for example, you may not have enough evidence to draw the generalization that there is a rule unifying them all. As you acquire new nouns, that regularity will become more and more evident, and the posterior probability on that generalization will become very high. That's one part of constructivism. So that is that as data accumulates, you can actually have regularity emerge from that. And the second constructivist insight is that with large data, you can also learn arbitrary idiosyncrasy. That is, that learning the rule does not cut you off from maintaining an idiosyncrasy on top of that. So those are things that I think are nice and compelling about this framework. And within that framework, what I want to do is I just want to give a few case studies of work that I've been involved in with students and collaborators on 3 different topics, which are all sort of generally around this. And I would describe them very briefly as follows. So the first one is really going to be simply a proof of concept of a relatively complex domain in learning of linguistic structure that has historically been approached from a parametric perspective, where we define a sort of a universal set of possible structures, possible languages, and we're going to just do proof of concept that you can actually have a more emergentist hybrid kind of approach. The second thing I want to do is and this connects with, I think, something that was raised yesterday, is to try to characterize this notion of the simultaneous existence of regularity and idiosyncrasy, characterizing the state of adult knowledge in a domain where these two sort of seem to interestingly sort of live in tension with each other. We're going to look at multi-word expressions to do this. And then finally, we're actually going to go back to the example that Caroline very briefly covered yesterday, which was the emergence of syntactic generalization in young children in the construction of noun phrases from determiners and nouns. So we'll look at how children use determiners together with nouns and what evidence that seems to give us about the state of syntactic productivity at various points in a child's life. So to start off with, I'll just very briefly talk about this non-parametric model. This is the area of learning phonological constraints. So the leading theory of phonological knowledge is probably optimality theory. And optimality theory, if I were going to summarize it very briefly, I would say that what a phonological grammar is well, there's one component which just says here is an inventory of forms and a mapping of possible underlying forms to possible surface forms. Above and beyond that, the grammar is a set of constraints that determine a mapping of a given underlying form to a preferred surface form or forms. So an example, this is wool of vowel harmony. So the input, this is a hypothesized underlying form, ite. And here are four constraints that are commonly assumed to govern the preferences and how this underlying form is realized in a surface form. So the four competitor surface forms that are under consideration are ones which basically have longer or shorter vowels. So there's ite, ite, ite. And there are four constraints that govern these preferences. Two of them are what we'll call markedness constraints. So those are constraints that just say certain kinds of surface forms alone are good or bad, relatively good or bad. And then there are faithfulness constraints which say that there should be a preservation of properties mapping from the input to the output. Okay, and the different kinds of constraints are, when they're violated, it's because there's something systematically bad in the output or because the output deviates from the input in some way. Those are the two characteristics. And you can make this a quantitative model. So previous work has done this. You can make this quantitative by giving the constraints quantitative weights. So this might be a way of weighting the constraints that's basically qualitatively consistent with the exposure that we get. You can then sum, for example, so every possible candidate has a badness score, which is the sum of the constraint badnesses that it violates, and then the least bad competitor is highly probable or is obligatory. So now, that's the backdrop. The question that I want to focus on is how does learning happen in this domain? So the traditional model of optimality theory learning is that there is a universal inventory of constraints, and that is given. That is that this is a parametric model, as I described in the earlier sections. So the constraints are given. There are no, and the only thing you can do is determine the relative importance of the constraints that are available. So all languages have the same constraints. The learner starts off with a particular constraint inventory. And the learning problem is simply to acquire ranking. Once you start looking at this problem seriously, there are a number of concerns that one might have. One is that the number of constraints required to account for rich cross-linguistic data may be immense. Another is that that specific languages may have very, very highly language-specific constraints. Now, how to get the best account of a phonological process in a given language that's the bread and butter of a phonologist. And for any individual question, for any individual problem, it's hard to know a priori how specific the constraints are that you're going to need to solve it. What we simply want to do here is we want to show that actually there is another way of learning optimality theory grammars that gives you the kinds of solutions that phonologists seem to think are appropriate for traditional phonological learning problems, but is not a parametric model. That is, it does not assume a universal constraint inventory. Rather, what we're going to assume is it's similar. The most similar work I think before us is the work of Hayes and Wilson on phonotactic learning. What we will assume is an inventory of building blocks for constraints, and we will use a non-parametric model that allows you to jointly induce both what the sets of constraints are, what constraints are active in a language, and what their ranking is. And we're going to do this in all of these large-scale learning models. You always have to inject in a non-parametric model some kind of parsimony bias that basically prevents you from ultimately just memorizing data. The appropriate parsimony bias will push you gently towards generalizations, gently enough that if the data compel you, you can learn arbitrary complex structure that is highly specific. But that may never be merited by the data, and it will depend on the case. It'll depend on the data type. So how does this look qualitatively? So as you saw before in the Wolof case, so an individual datum from the optimality theory perspective is given by a tableau of this form, where there's an input x, there are a number of candidate outputs y, and there's a number of constraints, and there's violation profiles. This matrix has some stars in some places and it has no stars in other places. The constraints have ranking or more generally a weighting, and the constraints have some intentional content. That is, the constraints are not simply they're not simply a series of stars and no stars. They have phonological content. If you had multiple tableaux, this might be two different tableaux. So the data are basically this, but of course, what the learner actually has direct access to is the surface form, and well, maybe we can simplify the learning problem by assuming provisionally that they have access to the underlying form. Now, we're going to go one step further, and we're going to simplify the problem a little more by saying that we can assume that the faithfulness constraints, that is, the constraints that govern the regularity of the mapping between inputs and outputs, is known. That might be a finite limited set of simple functions that say, for example, don't arbitrarily delete or insert sounds. Ultimately, I think this will also wind up being more learnable, but we would need different tools to do it. What we're going to relax, though, is several things. So we will say that the markedness constraints, the actual phonological content of them is not known. The number of them is not known. And of course, since the phonological content of them is not known, that we don't know what the violation means. We don't know how many columns this part of the tableau has. We don't know what we don't know what the stars are, where the stars are and they aren't. And we don't know the relative rankings of all the constraints at all. Okay. And we will learn, what we'll do is we'll learn this red part of the structure in the following way, using Bayesian inference. So we'll learn the constraint contents, the ensuing markedness violation profiles of the constraints, and the weights of all the constraints, given data y. If you do Bayesian decomposition, this turns out to depend on how likely are the data given the structure of the matrix and the weights. How likely is this weight vector a priori? So some weight vectors, since weights are quantitative, some weight vectors may have different a priori likelihoods than others. How likely is this markedness, how likely is the violation profile of the markedness part of the tableau given the phonological content of the constraints? And then how a priori likely is the constraint inventory? That how likely is it that you would have the number of constraints you have, and how likely would it be that the constraints look the way they do? Many of these, if you're familiar with optimality theory, you'll think of as deterministic. So for example, in principle, what the structure of this matrix is given the constraint phonological content and these things is deterministic. Likewise, which constraint, given a ranking, the outputs may be deterministic. It turns out in practice, adding some noisiness to this makes learning a little more feasible, in ways that learning with basically strong probabilistic but non-categorical preferences is always better. Then there's the question is what is the content? So what does it mean to represent a grammar of constraints that is a set of building blocks of constraints? So what we're going to use is a simple probabilistic grammar over constraint definitions, and it will favor simple constraints. And so at the basis of it is a feature value pair, And that feature value pair is then coupled with, is bundled, so there can be many of these, and they're ultimately put into feature bundles. So this will say, this will pick out a class of, this will ultimately pick out a class of sounds and include and exclude another class. And then ultimately, these can be sequenced together. So the grammar is put together one or more sound sequence, one or more segmental positions, and fill them out with sets of features, smaller or larger numbers of features. And the grammar is will say that to the extent that you can make this structure small and simple, those will be high a priori likely constraints. So there's a favoring of simple constraints. There's also a favoring we will put in of a smaller number of constraints. Okay, so these are the kinds of parsimony biases that you need. And then you can ask, well, so for example, what is learned for the English plural from limited data? So if we just feed it the 25 most frequent countable nouns, what is learned about the English plural? This is the regular English plural rule. And so what I'm going to give you here is that these are two different learning runs where everything has to be learned, and one learning run where we actually set the markedness, we'll set the matrix star structure the same. So this is, if you know what does and doesn't violate constraints, can you figure out what the phonological contents of the constraints is? And this is, what can you do if you have to learn everything? And what I'm giving you is the most, these model always learns two constraints, which is basically the best solution for this. So this is the best, sort of the standard solution for this problem, that you don't want to have adjacent, so the English plural is governed by don't have adjacent voiced sounds, and also avoid strident sequences. And that actually gives you the English plural rule. There are alternatives which are extensionally equivalent that are learned when you're looking at just the English plural data. Actually, the featural solution is underdetermined. Perhaps more interestingly, that so what we find here is that this is a learning run that gives us an accurate solution for the set of nouns that we gave it, but we'd actually need to look at other English paradigms to fully rule out some false starts that this got, and this is an imperfect solution. So the point here is, from limited data you can approximate, but of course are not perfectly guaranteed, to get to solutions that are very similar to what we think of as standard solutions. So the high level point here is that although optimality theory has been thought of as a parametric learning problem in the learning literature, we can actually formalize it as a non-parametric problem. That is, we can simultaneously learn how many constraints, what the constraints are, and how they should be ranked. So I now want to give an outline of a second topic, and this is characterizing the knowledge that we as adult native speakers of our language have of multi-word expressions. And what I want to get at in this part of the talk is I want to get at what is the trade-off between, in terms of our representation of any, by virtue of what is it that we know that any particular expression in our language is actually part of our language? And I think this is a very interesting question for perspectives on nativism, because for any particular expression that you've heard many times in your life, you could say the reason that you've heard it is, the reason that you know that it's in your language could be because you have generative knowledge that allows you to construct that expression, or simply that you heard it spoken by English speakers and therefore you should trust that it's an expression in the language. That's sort of obvious with words, with individual words. But once we get into multi-word expressions of the right size, we can actually sort of get at the edge of that and look at really how what the gray boundary between using productive knowledge sources to represent bits of linguistic knowledge and using direct experience are. Let's do a vote. So seamstresses and bishops, or bishops and seamstresses. Who votes for seamstresses and bishops? Who votes for bishops and seamstresses? Okay, yes. So that's consistent with our results. That's a pretty strong preference. So you might ask, how do you know that? How did everybody know that? So let me give you.
We can't see the hands. You should
What?
summarize which.
Oh, geez. Sorry. Sorry. Well, so you don't know that everybody else knew that bishops and seamstresses was I'm sorry. Yeah. Thanks. Yeah. So most of you preferred bishops and seamstresses. It was about 75-25, 80-20. Okay. So why do you have that preference? So there are many reasons why you have that preference. So you might prefer this because you're biased toward, for example, in these multi-word binomial expressions, placing culturally more powerful or central words that refer to culturally more powerful or central entities before less powerful or central entities. So bishops have a lot of social power, more so than seamstresses. You might have preferred it because you like short before long. So bishops is a shorter word than seamstresses. You might have preferred it because bishops is a more frequent word than seamstresses. And you might have preferred it because the ordering bishops and seamstresses minimizes the number of consecutive unstressed syllables. So bishops and seamstresses. So and that was 5. Seamstresses and bishop. Well, no, sorry, maybe that's bishops and seamstresses. No, it's 4 versus 5. Yeah, I'm right. It's 4 versus 5. Okay, so let's do a second example. Okay, meat and potatoes, or potatoes and meat. So raise your hand if you say meat and potatoes, and raise your hand if you say potatoes and meat. So very strong. Okay, so why do you think that that was meat and potatoes? In case you weren't sure. So why do you have this preference? So you might prefer meat and potatoes because it puts culturally more powerful or central before less powerful and central things. In particular, there's an example. This is an instance of what's called the condiment rule that Cooper and Ross originally identified. That says, you say, hamburger and fries. You don't say fries and hamburger, and so forth. It's highly general, and it seems to be subsumed under this sort of centrality idea. You might have preferred it because it puts a short word before a long word. You might have preferred it because the word meat is more frequent than the word potatoes. And you also might have preferred it because it minimizes the number of consecutive unstressed syllables. So meat and potatoes, so there's 3. Potatoes and meat. Wait. Shoot, okay, never mind. You might not have done it for that reason. At any rate, or you may prefer it because, of course, you've heard meat and potatoes far more often than you've heard potatoes and meat. Right? So the knowledge that this is a preferred order is crucially overdetermined by virtue of a set of productive knowledge sources that we can show are generally applicable, and on the one hand, and your direct experience with a multi-word expression on the other hand. And this is the vast majority preference. Okay, so these are instances of the binomial construction X and Y, where X and Y are lexical categories. So other examples, this would be salt and pepper, hit and run, gold and silver, chicken and egg, skirts and sweaters, bishops and seamstresses, few and unfavorable. Okay, and these are in a decline of relative frequency. Theoretically relevant features. So of course, these are all cases originally of productive syntactic combination. You've used the word and to combine 2 lexical categories. And furthermore, they're a wonderful source of investigation of, they're sort of a crucible for all sorts of things that you might find interesting about language. Every occurring binomial is a result of a speaker's choice about the ordering. And in fact, another beautiful thing about them is that now that we have big data, we can actually approximate how often an individual has experienced a particular binomial in both orders, and the relative preference of the orders. So this is the US Google Books N-gram counts. This is a US-centric presentation. I think most of the things will actually still apply. Principle and interest and skirts and sweaters are relatively equibiased, but they're not equally equibiased. Salt and pepper is overwhelmingly preferred in this order, although 200 years ago it was preferred in the opposite order for reasons I still don't know. And gold and silver is fairly strongly preferred in that direction. And then if you divide this, so a college level native speaker has about 350 million words of experience in life. So if you divide these by 1,000, you start to get a rough estimate of the number of times that you've heard each of these in each order. Okay, and so that will range from, many, many dozens of times. This is probably overdone, an overestimate in books, but many, many dozens or hundreds of thousands or thousands of times to probably never. Okay. And there have been many, many constraints that have been used to investigate that have been investigated as possible sources of productive ordering preference. Perhaps the strongest one that exists is iconic scalar sequencing. So that is the generalization here is that what happens first comes first. So if I say I open and read a book, that's not strange. I read and opened a book is. A hit and run in an auto accident is definitely where the person gets hit and then the car runs away. However, even this very strong constraint is a defeasible constraint. So for example, a hit and run play in baseball, if you know baseball, is one where the runner runs right before the batter hits the ball. Okay. So another constraint. Yeah. Okay. Well, then maybe nobody knows baseball. I don't know. Anyway, so the perceptual markedness says things like animate, concrete, positive things come before inanimate, abstract, negative things. The power constraint says more culturally prioritized or powerful words come first. The condiment rule is a special example of this. And then formal markedness says that words have a more general or broader meaning. If those words tend to come first. So sewing and quilting. Quilting is a special type of sewing, for example. And then there are some non-semantic constraints too. So there's this idea that the final syllable of the second word shouldn't be stressed. So this creates some preferences. More frequent words comes first. And then Panini's law says shorter words precede longer words. Okay. So I want to show you, so over many years, I've done a lot of work on building models that predict binomial ordering preferences. And the way that the simplest models that we've done look like this. So we'll have, for any particular binomial, we'll have a bunch of these predictors. We pass this through a logistic activation function. So there's basically like a simple regression that happens. And then that regression is converted into a 0 to 1 probability. And that determines a generative preference for the particular binomial's ordering. You can look at a lot of the features, even in a relatively small data set. A lot of the features that we use come out as clearly having the predicted effects. Some of them it's not so clear, and then they do a reasonably good job of predicting binomial specific ordering preferences. So this is what we actually observe. These are the model predictions. Okay. So overall, we can do a decent job of predicting systematic preferences. However, this is clearly not a perfect model. Okay, so a perfect model would be all of the binomials on the x equals y line, right? But actually, there's a lot of spread here, and in particular, for any different model predicted proportion, there are a lot of different values that we actually see in the corpus. Okay, and that's not just noise. That's like there really are differences. Now, one reason might be that our model isn't that great. You know, it's capturing some things clearly, but it might not be capturing that many things that we want. That is that we have an imperfect model of the productive knowledge. But another reason may well be that, well, above and beyond that level of productive knowledge, there are simply idiosyncratic preferences that individual binomials have. And so the noise around x equals y, a lot of it might reflect simply that binomials deviate in arbitrary idiosyncratic ways that are now accidents of history. And so let's think about that possibility. So this goes back to this second notion of hierarchicality. Now there's a hierarchical component to this productive knowledge that we have, but above and beyond that, you can accommodate arbitrary new binomials and represent their idiosyncratic preferences that deviate from that productive knowledge. So if adults have gone through the acquisition process by being hierarchical non-parametric learners, they should do a couple of things. So they should be able to apply generative knowledge in novel expressions. And they should also be able to rely increasingly on direct experience the more that experience is available. And so I'm going to show this first through a binary forced choice experiment that Emily Morgan and I did. And it's a very simple kind of experiment. We embed these binomials in what we hope are very neutral sentence frames that they themselves shouldn't perturb the intrinsic preferences the binomials have. So hopefully this is sort of a vanilla enough kind of sentence that it gives the idea. There were many bishops and seamstresses in the small town where I grew up, or there were many seamstresses and bishops in the small town where I grew up. And we did this for novel binomials like these that we can confidently say nobody has ever heard before who did not listen to one of my talks. Because you look in corpora and you see that they either never happen or they happen so infrequently that it would be vanishingly unlikely for an individual to have seen these expressions. So we do this for novel binomials, and we also do it for tested binomials of a range of frequencies. So this is what we get for novel binomials. And this is, I'm plotting the model's predictions versus human behavior. And even with a small number of novels, we see there's a very strong effect. So people are very clearly using the abstract knowledge that, that our model encodes. So, so we get pretty clear effects that people are able to use these general principles for novel cases. And this is not the first time somebody's shown this. So Pinker and Birdsong actually in 1979 showed that you got phonological ordering preferences on novel binomials as well, even nonce words, in fact. But here, I think more interestingly, is what we see for attested binomials. And to walk you through this graph, what I've done is I've binned the attested binomials into 3 levels of what I'll call overall frequency. That is the frequency, the sums of the frequencies of the 2 orderings. So it's just the overall number of times I've seen bishops, the gold, silver coordinated together in a 3-word binomial expression. These are the lower frequency ones, these are the middle frequency ones, these are high frequency ones. The shading on the dot indicates the overall preference, and by arbitrarily we've chosen alphabetical ordering as sort of a success outcome. So dark dots are ones that are chosen overwhelmingly or largely in alphabetical order as the preference, and light colored dots like this are mostly chosen in non-alphabetical order. And then the shading on the back is if we use the model predictions, if we use the model predictions on the one hand, and we use, that's been cut off over there, but here you can see it. This is if we just look at corpus proportion. This is what we actually find in a corpus. What you see is that as the overall frequency of the binomial expression goes up, so the Klein says, a sideways Klein says that, that people are sensitive to the general productive principles, like length and so forth, but not sensitive because it's not a vertical Klein, not sensitive to corpus frequency. As you go up higher in frequency, you can see the Klein becomes more diagonal, so there seem to be sensitive to both. And as you go into the highest frequency expressions, people seem only sensitive to corpus frequency. So that is, as you go along in this direction, as you have more and more experience with a binomial type, an unordered binomial type, you rely increasingly on your direct experience with the binomial and less upon the generative knowledge that forms overall the kinds of preferences you would have for a binomial that you would never have encountered before. And we can see this in a multiple regression. So just to give you an example. So for example, this directness and truth is this one, just to give you a sense of like what some of these things are. So this is one where the model actually predicts it's probably going to be truth and directness, probably for weight reasons, but it turns out that directness and truth is what people like. So there are some, there are some real discrepancies, but even within this discrepancy, that's a case where directness and truth is the more common example. So what we find is that actually both of these predictors have significant effects on low frequency preferences, but the size of the effect is much larger from generative knowledge. But as we move to more and more frequent expressions, the role of generative knowledge becomes less and less clear, and the role of direct experience becomes stronger and stronger. So what we see here is that from this, we've seen evidence that binomial-specific ordering preferences have cognitive reality for speakers. Just to summarize what we see here. And furthermore, there is a trade-off between what my general model of the world of binomials in general says should be the preference and what I know about this specific binomial. And that's exactly what a rational non-parametric language learner would do. They would start off by using generative knowledge, but actually learn the idiosyncrasies at the same time. Okay, this leads to a second question we can ask about binomials, which is simply what is the nature of the deviations from the generative knowledge preferences? So for example, why, of course, the fact that directness and truth is more common in that order than the model predicts, that is an individual fact of idiosyncrasy. But can we say more generally about the idiosyncrasies? And how can we furthermore, I haven't shown you how to model explicitly both generative knowledge and idiosyncratic preference. And so to do that, I want to show you a summary property of the distribution of binomials in English. And then let's just think about what this means. So this is a sample of several hundred binomials that we have. And this is the proportion of the binomial types, that is the proportion of the unordered binomials that have fall into a particular band of frequency of falling in alphabetical order. So here we have, these are binomials that always appear or almost always appear in alphabetical order. These are binomials that always or almost always appear in opposite to alphabetical order, and these are ones that are pretty mixed. And you'll see this has an interesting multimodal distribution. So there are lots of binomials which are pretty much 50-50 in English corpus data. And there's a reasonable number that are what we call frozen in the linguistics literature on binomials. They really pretty much only take one ordering or the other. And there aren't that many that are in between. Okay, there's a fair number, but there aren't that many. So we can ask the question, well, I have a model that I showed you of binomial ordering preferences, and what does that model say is the distribution? And the answer is that the model that I showed you does a terrible job of predicting that distribution. Okay, it doesn't say that binomials should be frozen at all. Okay, and so we've clearly done something wrong. Okay, so ordering preferences actually depart dramatically from generative knowledge. And what I've done wrong so far is I haven't introduced that level of hierarchicality that I talked about near the beginning. I didn't introduce that notion that there are central tendencies, that all of these different factors actually do push us around in different directions, and we can see that in bishops and seamstresses, how we respond to that binomial. But above and beyond that, binomials can also live their own lives in the lexicon of the language community and acquire, perhaps by chance or perhaps by for historical reasons, preferences that depart from those. In fact, the fact that those preferences depart sort of allowed us to even ask the question about how the two play off against each other in the previous section. So we need to augment our model with that notion of idiosyncrasy, and we'll do this. So this is what we did before. So this is a general logistic regression. So this is the part where we do something that's like an ordinary linear regression, but then we pass the result through the inverse logit function. And what we're going to do is we're going to just make this a little more complex by adding a beta binomial component. And the beta binomial component, so I think some of you are probably familiar with this component. I will explain it for those of you who are not. This part and this part are the same. Okay, so we have the linear regression-like part, we pass it through a logistic function, we get a probability that's a number that's interpretable as a probability. The additional beta component says then, around that average, we will then disperse probability mass on the span from 0 to 1. And we will do it in higher or lower dispersion levels depending on this parameter nu. A high value of the value of nu, which you can call a concentration parameter, when nu is high, the probability mass is focused on or around the vicinity of this value. When it's low, it's spread out more. And then the probability of an individual, and every individual binomial has, in the generative model, has a preference, an ordering preference that comes from this distribution, and you can use that to fit data. Here's what the beta distribution looks like. So all of these are cases where the mean is 2/3, okay? But there are different values of nu, the dispersion parameter. The legend didn't show up. So this is nu equals 30, so this is a very high concentration. And you'll notice that in this case, the probability of a particular binomial preference landing anywhere is highly focused around 2/3, the mean. As you go down to nu equals 6, it's more dispersed. As you go down to nu equals 3, it's a line. And once you have lower values of nu, it actually looks sparse. That is, that it predicts that there's a strong tendency toward freezing. Okay? So this is a way of describing the distribution of binomial preferences within a given level of overall average preference. So furthermore, we're going to do one other thing. So I just had this idea about binomials living lives in the mental community, in the community of speakers. Well, of course, that can only happen if the binomial is used enough to actually have its idiosyncrasy transmitted. So what I want to do is I want to say that concentration parameter actually could vary as a function of the overall frequency of the unordered binomial. And we could vary it parametrically to say that this concentration parameter depends on this overall unordered frequency in a relatively systematic way, or we can do it non-parametrically. So our complete model now has this constraints component. It has, that constraint goes through logistic activation to form a generative preference, but then that is layered on top of with this beta component. And that beta component has crucially an idiosyncrasy level, where low means low means lots of idiosyncrasy. I have that backwards. Low nu is lots of idiosyncrasy. And that we use to predict data. And now Bayesian data analysis, we say, well, we want to draw inferences about things like the actual binomial specific preferences by Bayes' rule. We can do that for all different components of this model. So the first thing I want to show you is what we find out about the overall distribution of binomial ordering preferences as a function of frequency. The more frequent an overall binomial is, the lower its concentration parameter. Okay, so that is, the more sparse the distribution is. So you may remember, with a high distribution, the actual preference tends to be close to the actual predicted mean, tends to be close to what the generative model predicted, the generative knowledge sources predicted. However, as you get more and more frequent binomials, that you have more and more experience with something, it can maintain a greater degree of preference. Okay, and that's true in the parametric version and the non-parametric version of the model. We can also ask, how well does this actually predict, do best guess prediction of individual binomial preferences? And well, this probably doesn't look any better, does it? So it actually is a little better. So you saw this before. I'll tell you what's better about this is that we're actually closer to the x equals y line. You can sort of see it's subtle. This is not an overall win. I mean, it's a win. It's not an overwhelming win. What is an overwhelming win is the distribution of binomial preferences in the population. This is reality, and this was our old model. This is our new model. So we've now recovered the multimodal distribution. Okay, and so what we found now, to sum up the binomial stuff, we've shown that first of all, strong inductive biases drive ordering preferences even in novel binomials. So we saw that in our very first experiment on this. But as direct experience increases, speakers rely more and more on it. And these frequent binomials can also retain stronger idiosyncratic preferences in the community of speakers. And this is exactly what we would expect from these non-parametric hierarchical models. There's a layer of generalization that's extracted out, which is general preferences of ordering. Above and beyond that lives idiosyncrasies, and those idiosyncrasies can be learned and retained more systematically and more thoroughly through time and in the minds of individual speakers with greater frequency. Okay, so I have 5 minutes left, I'll do an abbreviated version of this last part, but I definitely don't want to skip it because it connects up with the stuff that Caroline had talked about yesterday, and I think it really is. It also speaks very much to the topic of the workshop. So this is about it's about acquiring syntactic productivity. So we've already seen that adult native speakers have detailed memory for specific multi-word expressions, and also they can use abstract knowledge to combine new multi-word expressions. So what I want to do is I want to ask, how does this combinatorial potential emerge developmentally, and what's its relationship between that combinatorial knowledge and then specific item-based knowledge? So this once again is coming back to the in practice sort of testing grounds of empiricist and constructivist and nativist accounts. And we're going to look at noun phrase combination, nouns and noun phrases combining from determiners and nouns. And Caroline introduced this, but just to reiterate, an adult native speaker knows that A and the are words of the same category, and this category can combine freely with nouns. Okay, and so that we know that that's the end point of acquisition. The question is, what is the developmental trajectory of that productivity? And I want to lay out the two poles that have been defined, and this is really it's a very clear case where the nativist and the constructivist camps have, at least started out with relatively clearly differentiated positions. So just to sort of draw caricatures, I'll describe the rule-driven child. And the rule-driven child has, their knowledge constitutes it's simply these syntactic rules. And you could put rule probabilities on the syntactic rules that allows you to make predictions about aggregate behavior. This view of the child generally argues that this kind of productive knowledge emerges very early and is associated with people like Virginia Valian and Charles Young. And then there's the item-driven child, where I would describe sort of the experience that one has with the child under this view is as follows. The child is awash in a sea of input. Out of that input, it's able to extract some islands. Those are islands that it remembers. And early on in its multi-word productivity, it will reflect what it was able to, the bits of input, the islands that it was able to extract out of the input. And productive knowledge will emerge only gradually after this point. Okay, and this is associated with figures like Pine and Levin and Tomasello and Caroline and other kinds of work, and not on determiners. Now, this has been a very interesting area in which people have. I mean, I would actually disagree with Caroline in the following way. So Caroline said, you know, people are actually now in agreement in the field about how to deal with this problem empirically. I actually think the thing that's a little troubling, I'm sure you agree about this, is that the good side is that people sort of agree on the kind of corpora and data sets to look at. The bad thing is that people are looking at the same qualitative types of data sets and drawing opposite conclusions based on details of how they do data analysis. So the overlap score, which Caroline described, is the standard now that people seem to be using. And here's the way that empirically the overlap score works. You look in a corpus of, say, a child's productions or an adult's productions. There will be some subset of nouns that were used at least once with the word a. There will be another set of nouns that was used at least once with the word the. Some of these nouns will be in both sets. And then just basically it's the set of nouns here, the sum of the set number of nouns in here, divided by the number of nouns in this whole area. That's the overlap score. As Caroline pointed out, this score is hard to use because most nouns are low frequency. So in the same year, in 2013, we had Charles Young putting out a model, a very, very simple model of the productive child, and saying children look perfectly productive. And using very similar types of data sets, Pine et al. Concluded that productivity develops gradually on the basis of both on the basis of overlap scores. So what we're doing here is we're going to do something slightly different. And it focuses on the critical conceptual issue about the overlap score. So the overlap score is a summary statistic that reflects child or adult usage. However, what we're actually interested in is the source of knowledge that is being brought to bear in the production that is then being summarized in the overlap score. So really what we're interested in is we're interested in inferring the latent property of where on the item-driven to rule-driven spectrum a child is. And in fact, in the middle of that spectrum, surely one needs to have productive and item-specific knowledge, just like one has in binomial expressions. And you can see that from determiner cases. So determiner choice depends on context, and different nouns may tend to have different relations. Those contexts appear in different types of contexts. Give me a banana, give me the pear. If this is if you tend to be around fruit baskets that have multiple bananas, and you'll see bananas more so than multiple pears, A and the will be used with different frequencies. Likewise, there are simply idiosyncratic determiner preferences for some nouns. So you catch a cold, but you catch the flu. Right. And so we want to represent these we want to have this same sort of hierarchical notion of different levels of generalization. So what we're going to do is we're going to explicitly represent the roles of direct experience and of the generalized productive knowledge of how determiners and nouns can be put together. And we'll formalize a model of this, and it'll look a lot like the last model. And what we'll do is we'll then use human data. We'll use child data, and also, and this is something new that we're doing as well, we're using child data and the relationship with caregiver data to infer to infer with what confidence can we say what about what the child is bringing to the table above and beyond the direct experience that it has. And so what we're ultimately going to look for is we want to have, this is sort of our pie in the sky graph, we want to have from the time that the first multi-word utterances of child emerge all the way to adult competence, well, we already know the adult competence is sort of this non-parametric combination of item-driven and rule-driven knowledge. And we want to know how the child gets from here to here. And there are lots of ways this could look. So productivity could gradually develop. It could look like this. Productivity could emerge very early and then sort of level off. Children might even go through an early overgeneralization phase in determiner usage, like they do, for example, in morphology. And you could also have all sorts, who knows, right? We want the evidence to actually draw us this picture. Maybe it looks like something really weird. We don't know, but we want the evidence to actually be able to speak to this. So our two knowledge sources for determiner preference looks like this. So there's the child's productive knowledge, and you'll recognize mu, not, and nu. This is like the same mu of the binomials. This is, on average, how much is the liked versus and then how variable are nouns in their idiosyncratic preferences. Above and beyond that, the child actually learns from caregiver data. So the child, we as the experimenters, as the researchers, we have observed some fraction of the caregiver data, and we can treat the remainder as latent variable that we have to impute. Furthermore, children may be more or less efficient at actually remembering and learning from caregiver data. So there's a parameter, we'll think of this as a learning noise parameter. And if this actually turns to be pretty important in the model for reasons that I can describe a little later if you want. And so this is the direct experience component. This is a productive knowledge component. In practice, we define this as a beta prior, like I described before, and this is beta binomial update. So this actually is a lot like the binomial model we talked about before, but it has this additional learning from data component directly. Let me actually just, I want to describe, if we think about the spectrum of the item-driven to the rule-driven child, there's also this, a child can be an efficient or an inefficient learner, that is, learn quickly from evidence or learn slowly from evidence. And here's just some examples of the kinds of regimes that we expect to see. So over here, if the child is a very strongly rule-driven child, regardless of how efficiently they learn from data, what we're going to see is that the child tends to produce the same A patterns with all of the determiners. So if it's 50-50, they're going to produce 50-50. This actually is basically, in the limit, this is Young's model. On the other hand here, so that's the strong overgeneralizer. The child does not learn the fine details of experience with some specific nouns. Down here, there is a regime which is an efficient learner from input. So they basically, for a particular noun, they move over their preferences in a way that is consistent with the input because their tendency to generalize across nouns is not that strong. Here we have an island learner. Okay, so an island learner is, crucially, they can't learn, they can't have picked up every single instance that they ever got because otherwise they probably would have gotten both. But if they are getting some fraction of the instances of them and they don't have a strong tendency to generalize, then we'll see it's very likely that they might only be able to produce a particular noun with only one determiner, not the other. And then here we have, this is sort of a vanilla generalizer who doesn't learn super fast, but also has a reasonably strong tendency to generalize. Okay, so there's basically 4 qualitative regimes that we can see. This is just to give you a sense of the kinds of, how to think about the results that I'm going to show you now. Okay, so we'll skip that. Longitude and nature of the data sets. This is something I want to emphasize. So we've tried to cover a superset of what everybody else has covered. People have used different corpora. Brown, Manchester, and Providence corpus are all corpora that have been used by other researchers. You can see the density and age of the different corpora. We also are very lucky to have access to the human speechome data set, which is the largest single recorded data set of child-directed and child-produced speech that exists. It's done by Deb Roy in the Media Lab. And what you see strikingly is, first of all, this is before the age of 2, we have a remarkable amount of data from the child. Maybe even more striking, we have a remarkable amount of data from the adult. So this allows us to get a much stronger sense of exactly what the child did and may not have heard. And then that puts us in a better position to infer what does actually each production tell us about the child's productivity level. Of course, you're not going to find any individual smoking guns in a corpus that say, this is for sure, this individual utterance for sure shows the child is a productive noun phrase constructor. But there's yeah, sure.
Can you actually tell what determiner they're producing in those really early files?
No, so this is total input, but yes, this is actually, sorry, that's actually a good point. Actually, most of this is false positives that we've thrown out since. Yeah, thank you. Actually, that's a good point. Yeah. So it's really sort of more like here. Yeah, good. And what we do, so this should really be about here. So what we're going to do is ask, has productivity changed over time by comparing the new inferred value in the 2 parts of each individual's speech. So here's sort of our overall results graph. And it's very complicated. The vertical lines are confidence intervals. So this is, each of these dots represents half of an individual's data. You can see that there is a lot of variability, but you can also see what the sort of highest inferred new values are. There are not any clearly strong overgeneralizers in this data set. In general, children seem to sort of reach this consistent value of 0.7 to 2 in this region. It's not clear what's going on over here. I guess of particular interest is the speech-home child because we have so much data for the speech-home child. Here is a sort of first versus second half comparison of has the productivity level changed over time from the first half of an individual's data to the second half of an individual's data. There are only two children for which we can draw high confidence inferences that there has probably been a change in one direction or the other. That's the speech-home child who seems to have gained in productivity from early to late. And then there's this other child, Thomas, who seems to actually have dropped in productivity from early to late. I would say the overarching result is that we cannot draw strong inferences. It's very, very hard to know exactly whether there's a consistent tendency. For most of these data are 2 to 3.5. But we can say, these are for the earliest children, at least for the child where we have a lot of data, there seems to be some possibility that the child started out very unproductive and wound up more productive. And maybe there's decreasing productivity later on too. We don't know. Sorry? I believe so, but I should check afterwards. He's really slow. Okay, well, this is got less productive in the second half of his time, not is overall unproductive. So, yeah, okay. This is interesting observation. Okay, and then we can do exploratory visualizations to sort of see. This is a windowed analysis. Not all of these are not statistically independent from each other, but you just sort of get a qualitative. These data points should be thrown out. But there does seem to be a rapid rise in productivity of the speech-home child from extremely unproductive to more productive in the later stages of the data set. If you look at most children, basically what you find is that simply there's not enough data to draw strong conclusions. So what we've done here, I think from a modeling point of view, which in a way I feel like is the sort of highest level point here, is that we're now in a position to explicitly represent the joint contributions of these two different kinds of knowledge sources, of the productive knowledge on the one hand of a generalized combinatorial potential between determiners and nouns, and on the other hand, what the child has or has not learned from their direct experience. I think the main result that I would say is that for the most part, I think the data sets are actually too small to draw high confidence inferences. I might actually, and many of them, if there are developmental changes, maybe they're too late. So maybe there may be tantalizing suggestive evidence that if we're going to look somewhere more systematically for a transition from more island-driven determiner-noun combination to more productive determiner-noun combination, we want to look in the very earliest months of childhood of multi-word expressions. Once again, I would say it's very preliminary, but if it's anywhere, you would look at it in the early months of multi-word speech, and syntactic productivity emerges very soon thereafter. And then overall, I think just to wrap everything up, we're now able to represent these kinds of rich structured knowledge sources in language and cognition, and I think these models really do integrate both nativist and constructivist insights and allow us to construct more precise candidate learning theories, and we can also use the same kinds of models to analyze data sets, and we can actually get scientifically interpretable outcomes of our statistical analysis. So that is, the model that we're using to analyze the data is actually framed in a way that sheds light relatively directly on where, for example, human learners are on the continuum from a sort of strong nativist style learner to a strong constructivist style learner. So that's what I see as maybe the highest level appeal of where we are in this program. So I want to just acknowledge collaborators and data source people and funders, and more importantly than that, all of you. Thank you.